Have you ever peered under the hood of something you use every day and wondered, how does that really work? Today, we're doing exactly that, but for something absolutely fundamental to modern software databases.
Oh, yeah. Databases, they're everywhere.
Exactly. We're not just talking about how to query them, select star from whatever,
Hmm.
but how they actually store, retrieve, and manage your data, especially when it's spread across like tons of machines.
Right. The distributed aspect adds a whole other layer of complexity.
It's a world of really clever engineering that impacts everything we build, and we're diving deep today. Our mission, basically, is to give you a true shortcut to being well-informed on the core mechanics, the real guts of database systems. We're drawing our insights from Alex Petrov's incredible book, Database Internals, a deep dive into how distributed data systems work. Highly recommend it.
It's a fantastic book. Really gets into the weeds.
Yeah, and this deep dive isn't just for hardcore database developers. It's for, well, anyone who builds software that relies on databases. So software engineers, engineering managers, or honestly, just curious minds who love learning how things tick.
Absolutely. It's fascinating how understanding these underlying concepts, even just the basics, can dramatically improve your ability to troubleshoot. Identify risks, use your tools more productively. It's really about building a solid mental model.
A mental model, I like it.
Yeah, of how data truly lives and moves within these critical systems you interact with every single day.
Okay, let's start right at the beginning then. A database management system, a DBMS. It might seem like one big blob, right?
Yeah, it often feels that way from the outside.
But it's actually a highly modular system. Lots of distinct parts working together. Think of it like a finely tuned machine. Different gears meshing seamlessly. You've got a transport layer handling requests coming in.
Yep, yeah, network stuff.
A query processor to figure out what you're actually asking for.
Parsing the SQL, optimizing it.
An execution engine to actually carry out those instructions.
Doing the joins, the filtering.
And then right at the heart of it all, the storage engine.
This storage engine. That's where the magic really happens, I think. It's the software component responsible for the nitty-gritty details. Storing, retrieving, managing data, both in memory and on disk.
So it's the persistence layer.
Exactly. Its primary job is to give each node in your system a persistent long-term memory. You can actually view the entire DBMS as like an application built on top of this core storage engine. The storage engine handles the bytes, and the DBMS adds the fancy features like schemas, SQL, transactions.
So what does this modularity, this layering, what does it really mean for you, the listener? It means thinking of a database as just a black box is, well, kind of risky business.
Definitely risky.
Sooner or later, a bug, an outage, maybe a weird performance bottleneck will pop up. It always does. And understanding even these basic internals can significantly reduce business risks, help you get things back on track much, much faster.
Totally agree. Knowing which layer might be causing the problem is huge. And if we connect this to the bigger picture, one of the first fundamental design decisions is how databases handle memory versus disk.
Right, the in-memory versus disk-based distinction.
Yeah, both sides use disk, obviously, but where they primarily keep the data demands their whole architecture. In-memory databases keep most data right there in RAM. Super fast access. They use disk mainly for like recovery logs, writing changes sequentially just in case of a crash.
Okay, so disk is more for backup and durability there.
Exactly. Disk-based systems, on the other hand, keep most data on disk. Much larger capacity, usually cheaper. They use memory mainly for caching, keeping hot blocks, frequently accessed data, in RAM.
Okay, that makes sense. But it brings up a question, right? Why not just give a disk-based system a huge memory cache? Like tons and tons of RAM, wouldn't that basically make it in memory?
That's a great question. And the answer lies in the data structures they use. It's not just about the amount of memory. Disk-based systems use specialized structures, often described as wide and short trees, think B trees, which we'll get to. These are specifically optimized to minimize the number of random disk accesses, because random I/O is incredibly slow compared to RAM access.
Ah, okay, so the structures themselves are fundamentally different, optimized for disk slowness.
Precisely. Structures designed for memory, where random access is cheap, look very different.
Gotcha. Okay, this idea of data layout, it gets even more interesting when we think about how data is physically stored on disk, like row-wise versus column-wise storage.
Oh yeah, row stores versus column stores. A massive difference depending on your workload.
So imagine a typical user table, right? Name, email, phone number, all that stuff. A row-oriented system stores all the data for one user together, side by side on the disk page.
Yeah, Jane Doe's info is all in one chunk.
Mhm.
John Smith's is in another chunk.
Which is fantastic if you often need the entire record, like, get me everything about Jane Doe.
Perfect for that. OLTP, transactional workloads often benefit from that.
But what if your query is analytical? Like, give me just the phone numbers for everyone.
Uh-oh.
Yeah, a row-oriented system has to read all the data for every username, email, everything, just to pick out the phone number and discard the rest.
Super inefficient for that kind of query.
Yeah.
Lots of wasted I/O.
Exactly.
Which leads us to...
Column-oriented systems, they partition data vertically. So all the names are stored together, all the emails are stored together, all the phone numbers are stored together, contiguously.
Ah, okay. So for that all phone numbers query...
It's incredibly efficient. The system just reads the block, or blocks, containing only the phone numbers. Doesn't touch names or emails.
Perfect for analytics, data warehousing.
Exactly. Like fetching historical stock prices where you only care about the price column across millions of records. The source, Petrov's book, also mentions these advanced wide column stores, conceptually like Google's web table. They extend this idea using hierarchical indexes, grouping related columns into column families.
Column families, right. And even storing multiple versions of data, time-stamped. It's all about optimizing for specific, often analytical, access patterns.
Okay, building on that storage layout, let's unpack how a database organizes data internally. It's more than just dumping files on a disk, right?
Oh, much more. If you just dumped raw data, finding anything would mean scanning the entire thing every time. Terribly slow.
Yeah, forget that. So databases use these auxiliary data structures, indexes.
Indexes, exactly. Think of it like the index at the back of a textbook.
Perfect analogy. Helps you find specific topics, specific pages, without reading the whole book.
Precisely. So the system typically separates the actual data files, holding the records, from the index files. Index files contain metadata and pointers, basically addresses, pointing to where the actual records live in the data files.
And index files are usually much smaller.
Much smaller, yeah. Which means they're easier to cache in memory, making lookups faster. Now, the data files themselves can be organized differently, too, like heap-organized tables.
Heap tables, what's the deal with those?
They're simple, conceptually. Records are just placed in the order they're written, like appended to the end.
So writes are fast.
Writes can be very fast, yeah.
Yep.
Stick it on the end. But the downside is...
No inherent order.
Exactly. There's no inherent order. So reads, unless you're scanning the whole table, always need an external index to find anything specific.
So it's a trade-off. Fast writes, but reads rely entirely on having the right indexes.
It highlights that fundamental trade-off, yeah. Optimize writes, maybe reads suffer without help, and vice versa. Oh, and a crucial detail about modern storage, especially with SSDs and even disk systems. Databases don't usually delete data immediately when you issue a delete command.
They don't, so the space isn't freed up.
Not right away. They use deletion markers or tombstones, special flags.
Tombstones, okay.
It marks the record as deleted, but the actual data might stick around for a while. The space only gets reclaimed later.
By what?
By a background process, usually called garbage collection or compaction. It tidies things up, reclaims space from tombstoned records.
Gotcha. Okay, so beyond just files and indexes, the book mentions 3 core principles that shape storage structures.
Right. Buffering, immutability, and ordering. They're fundamental concepts.
Let's take ordering. You mentioned heap tables being unordered. What's the alternative?
The alternative is storing data records in key order on disk, like in the leaf pages of a B tree.
And the benefit there is?
If the data is physically sorted by key, scanning a range of records like find all users with IDs between 1,000 and 2,000 becomes super efficient.
Because they're all next to each other on disk, sequential reads.
Exactly. Sequential reads are fast. But inserting data in the right ordered spot can be slower than just appending. Trade-offs again?
Always trade-offs. Okay, so how are these structures like ordered data or index nodes actually put on disk?
Physically, the answer is pages. Database files are partitioned into these fixed size units. Pages.
Fixed size, like how big?
Typically somewhere between 4 kilobytes and maybe 16 kilobytes, sometimes larger. These page sizes often align with the underlying file system block sizes or multiples of them for efficiency.
Okay, and things like B-tree nodes, they live inside these pages.
Yep. A B-tree node often occupies 1 or more pages. So you'll often hear people use node and page almost interchangeably in that context.
Right. The page is the basic unit of I/O. When the database reads from disk, it reads a whole page.
Correct. It doesn't read individual bytes usually. It brings in a whole page at a time.
Okay, but what about data that doesn't fit neatly, like variable size stuff, Big text blobs, images, JSON documents, maybe?
Ah, good question. Fixed size slots within a page would be super wasteful for that. Lots of empty space. So databases use a clever technique called slotted pages.
Slotted pages, how do they work?
A slotted page has a fixed size header with metadata about the page. Then there's an array of pointers, or offsets, usually growing from the end of the page inwards.
Uh,
And then the actual variable size data cells are stored in the remaining space, maybe growing from the start of the page outwards.
okay, so the pointers tell you where each cell starts within the page.
Exactly. The pointer array gives you the location. This allows for minimal overhead. You can efficiently reclaim space by just shuffling cells and updating pointers, defragmenting within the page. And the system can reference records just by their slot ID without needing to know their exact physical byte offset, which might change.
Clever, very flexible.
It's all about packing data efficiently onto those fixed-size pages.
Okay, one last piece on this foundational stuff. Ensuring data integrity. How does the database protect against, like, random bit flips on disk? Corruption.
Yeah, silent corruption is a scary thing. Databases use checksums for this.
Checksums, like an MD5 hash or something.
Sort of, but usually simpler and faster algorithms optimized for this purpose. Doing it over an entire huge file is too slow and impractical, so they do it at the page level. Each page has a checksum computed from its contents, and that checksum is stored right there in the page header.
Ah, so when the database reads a page,
It recomputes the checksum from the data it just read and compares it to the checksum stored in the header.
if they don't match.
Bingo. You know that page is corrupted. Maybe a disk error, a power surge during a write. Something went wrong.
And you can detect it immediately rather than finding out later when the data makes no sense.
Exactly. It allows the database to potentially recover that page from a replica, or at least report an error, instead of having the corruption spread or silently ruin things.
What kind of checksums?
CRCs, cyclic redundancy checks, are very common. They're particularly good at detecting burst errors.
Burst errors.
Yeah, where multiple consecutive bits get flipped, which is a common type of error in storage and transmission. CRCs are mathematically designed to catch those well.
So it's like this silent guardian constantly checking the health of your data at the page level.
Vital. Absolutely vital for data integrity.
All right, let's shift gears a bit and unpack one of the most, truly foundational data structures in databases, the B tree.
Ah, the mighty B tree. Introduced way back in 1971. Still incredibly relevant.
Yeah, amazing longevity. They were specifically designed for disk-based storage, right? Not memory.
Correct. Primarily for disk.
So why couldn't they just use a regular binary search tree? We learned about those in basic computer science. They seem simpler.
Simpler conceptually, yes. But the core challenge B-trees solve is that slowness of disk access we talked about.
The random access penalty.
Exactly. Random disk I/O is orders of magnitude slower than sequential access and vastly slower than RAM access. Hard drives, even SSDs, access data in blocks or pages, not byte by byte.
Right.
A traditional binary search tree, which is tall and skinny, could require many, many pointer hops to find a leaf, each hop potentially being a slow, random disk read. Terribly inefficient.
Okay, so how do B trees fix that?
B-trees conquer this by being wide and short.
Wide and short.
Yeah. Each node in a B-tree, which remember typically corresponds to a disk page,
Gotcha.
can hold many keys and pointers to child nodes.
Ah.
Hundreds, maybe thousands, depending on the key size and page size.
So instead of just two children like a binary tree, it has potentially hundreds.
Exactly. This drastically reduces the height of the tree. Fewer levels means fewer disk reads needed to traverse from the root down to the leaf page containing your data.
Makes sense. Fewer hops, fewer slow disk accesses.
Precisely. And they also have another useful feature: sibling pointers on the leaf level.
Sibling pointers, linking the leaf pages together.
Yeah, the leaf pages are typically linked together in key order, like a doubly linked list.
Why is that useful?
It makes range scans incredibly efficient. Once you find the start of your range on one leaf page, you can just follow the sibling pointers to read the subsequent pages sequentially.
Without having to go back up the tree. Nice.
Very useful for queries like find all orders placed last week.
Okay, but keeping this structure balanced, especially with lots of inserts and deletes, must involve some work, right?
Oh yes. Maintaining a B tree involves splits and merges.
Splits and merges.
When you insert a key and a node gets too full, it has to split into two nodes. The middle key gets promoted up to the parent node.
Okay, that keeps it balanced but adds a new level sometimes.
Right. And conversely, if you delete keys and a node gets too empty, below a certain threshold, It needs to either borrow keys from a sibling or merge with a sibling node to maintain minimum occupancy.
To avoid wasting space and keep the tree efficient.
Exactly. This dynamic balancing ensures lookups remain fast, typically logarithmic in the number of records.
Are there variations?
Yep. Variants like B trees, for instance, try to improve space utilization.
B-star trees. How?
Instead of splitting a node immediately when it's full, a B tree tries to redistribute keys with a neighboring sibling first. Only when both the node and its neighbor are full do they perform a split, but they split 2 nodes into 3.
Ah, clever. So it postpones splits and keeps nodes fuller on average.
Right. Better average occupancy, which can mean slightly fewer pages overall and potentially faster reads.
Okay, let's talk about maintenance and deletes again. You mentioned tombstones earlier. How does that play out in B trees?
Right. Remember those deletion markers? In many B tree implementations, particularly on the leaf level where the actual data or pointers to it resides, a delete operation might just remove the cell offset or flag the entry.
It doesn't immediately shuffle everything around to reclaim the space.
Not always, no. This can lead to fragmentation within the pages.
Fragmentation, like holes in the page.
Exactly. You might have enough total free space on the page, logically, but not enough contiguous space to fit a new large record.
So you need to clean that up somehow.
Yes. This requires background garbage collection or page reorganization processes. These processes periodically read fragmented pages, rewrite them with the cells packed neatly in key order, reclaiming that scattered free space.
Like defragmenting your hard drive, but at the page level?
Kind of, yeah. And interestingly, some databases actually leverage this mechanism, keeping old versions of rows around for a while.
Why would they do that?
For multi-version concurrency control, or MVCC, it allows readers to access an older, consistent snapshot of the data without blocking writers who might be creating a newer version simultaneously.
Ah, okay. So the garbage isn't always garbage immediately. It might be needed by other transactions.
Precisely. Until it's certain no transaction needs that old version anymore.
Cool. Now here's another twist on B trees mentioned in the book. Copy on write B trees. That sounds different.
Very different philosophy. Instead of updating data in place on an existing page.
Which is what standard B trees usually do.
Right. Copy and write, or CowW, B trees treat their nodes as immutable.
Immutable, so you can't change them.
Once written, a page is never modified. If you need to change something on a page,
You make a copy.
exactly, you copy the page, apply the update to the copy, and then write this new version to a completely new location on disk.
And the old version just stays there.
It stays there, untouched. The pointers in the parent node are then updated to point to the new page instead of the old one. This cascades up the tree.
Wow. What are the benefits of doing all that copying? Seems like more work.
It is more work in terms of space and CPU, definitely.
Yeah.
But the advantages are significant. Firstly, readers never get blocked by writers, and they don't need complex locks. They could just read the old, consistent version while a writer is preparing a new one.
Okay, better concurrency.
Much better concurrency for reads. Secondly, crash recovery becomes much simpler.
How so?
Since you only switch the top-level pointer, the root of the tree, to point to the new structure after all the modified pages have been safely written to disk, a crash can't leave the tree in a half-updated, corrupted state. You either have the complete old tree or the complete new tree.
Atomic updates for the whole structure. Very robust.
Very robust.
Yeah.
The downside is potentially lower write throughput and higher space amplification due to all the copying.
Trade-offs again. Okay, building on that immutability idea. Lazy adaptive trees or LA trees?
Right, LA trees. They try to get some benefits of immutability while reducing the I/O overhead. The core idea is to buffer updates to nodes in memory.
Buffer them. So don't write them immediately.
Correct. Updates sort of trickle down through layers of buffers in memory. When they finally reach the leaf level, they're applied in larger batched operations, inserts, updates, deletes, all done together.
Ah, batching. So fewer larger disk writes instead of many small ones?
Exactly. Fewer direct disk accesses and fewer structural changes to the tree itself, because splits and merges also get buffered and propagated in batches.
Trying to optimize I/O by delaying and batching.
It's an evolution, trying to find that sweet spot between in-place updates and full copy on write.
Okay, so B trees in their various forms are workhorses, but they fundamentally rely on updating pages, often involving random I/O. What if we could design a storage system that, like, almost completely avoids random writes?
Ah, now you're teeing up log-structured merge trees,
Yeah,
LSM trees.
LSM trees. They take a fundamentally different approach, right?
Completely different. They embrace sequential writes and immutability.
How do they work? What's the core idea?
The core idea is to defer writing data to its final place on disk. Instead, all incoming writes, inserts, updates, even deletes are first buffered in a memory resident table, usually sorted, often a tree or skip list.
In memory. Okay, what's that called?
It's commonly called a mem table.
Mem table. Got it.
When this mem table fills up, reaches a certain size.
You have to flush it. Right.
Exactly. Its contents, which are already sorted in memory, are written out to disk as a new immutable file, a sorted segment.
Immutable, like the cow WB trees.
Yes, once written, these disk files are never modified. New data always goes into new files.
And how is it written? Randomly.
No, this is the key. It's written sequentially. A single, efficient pass writes the entire sorted mem table content to a new file on disk.
Ah, all sequential writes. No random seeks to update existing pages?
Precisely. This design strongly favors write performance, especially on rotational disks, but also helps with SSD write endurance. It contrasts sharply with B trees, where updating one record might mean rewriting a whole page randomly.
Okay, but now you've got potentially lots of these immutable sorted files on disk, right? From flushing many mem tables over time.
Yep, you could end up with a whole hierarchy of these files, sometimes called S-tables, sorted string tables, or segments.
So how do you find a piece of data? It could be in the active mem table or any one of those dozens, maybe hundreds of files on disk. Seems complicated.
It is more complicated for reads. That's the trade-off.
Right.
And the solution is compaction.
Compaction, you mentioned that with tombstones. How does it work here?
Compaction is a background process that takes several of these disk-resident sorted files,
Reads them in.
reads their contents, merges them together, just like doing a multi-way merge sort.
Okay, combining sorted lists.
Right. And runs the combined sorted result out to a new, usually larger, immutable file.
And the old files.
Once the new merged file is safely written, the old input files are discarded, garbage collected.
So compaction cleans things up, reduces the number of files you need to check during a read.
Exactly. It keeps the number of files manageable, merges older data, removes deleted or overwritten data, and generally improves read performance over time. It's absolutely essential for LSM trees to function well.
How are updates and deletes handled in this model if files are immutable?
Great question. They don't modify existing files. An update is really just treated as a new insert of the key with the updated value.
Okay, so the newer version just lives in a newer segment or the mem table.
Correct. And a delete is also just an insert of a special marker, a tombstone, for that key.
Ah, tombstones again, marking it deleted without touching the old data.
Exactly. So during a read operation, the database had to look for the key in the mem table and potentially all the relevant disk files, from newest to oldest.
And take the most recent version it finds.
Yes. It has to reconcile the different versions. If it finds a regular value, that's the current state. If it finds a tombstone first, the record is considered deleted, even if older versions exist in older files.
So reads have to potentially touch multiple places.
Reads have to potentially consult the mem table and multiple disk files, yes. This merge iteration process uses efficient algorithms, like a multi-way merge sort, often using a priority queue, min-heap, to combine the sorted data from all sources on the fly.
That sounds like it could still be slow if there are many, many disk files.
It can be, which is why LSM trees often use another clever trick to speed up reads, especially point lookups for a specific key.
What's that?
Bloom filters.
Bloom filters, those probabilistic things.
Exactly. Each disk resident file, S-table, often has an associated Bloom filter built from the keys within that file.
And how does that help a read?
Before checking a specific file on disk, which is slow, the database first checks its Bloom filter for the key you're looking for.
Okay.
The Bloom filter can definitively say this key is definitely not in this file.
Ah, so you can skip reading that file entirely.
Precisely. Saves a potentially costly disk access. Now, the catch is...
False positives.
Right. A Bloom filter might sometimes say, the key might be in this file, even when it's actually not. It never has false negatives, but it can have false positives.
So if it says maybe, you still have to check the file. But if it says definitely not, you skip it.
Exactly. It filters out checks for most files that don't contain the key, dramatically reducing the number of disk reads needed for lookups on average. Very space-efficient way to speed things up.
Clever. Okay, what about the mem table itself? That in-memory structure, is it usually a B tree?
It can be, but another very common structure used for the mem table is the skip list.
Skip lists, I remember those. They use randomness, right?
Yeah, they're a sorted data structure like a linked list, but with additional express lanes.
Hmm.
They use probabilistic balancing to create multiple levels of linked lists where higher levels skip over more nodes.
Allowing you to jump across the list quickly during searches.
Exactly. Makes lookups efficient, typically logarithmic time on average. And the key advantage over balanced trees like B trees.
Simpler implementation.
Much simpler to implement. No complex rotation logic needed to maintain balance like in AVL or red-black trees. The probabilistic approach handles balancing.
What's the downside?
Traditionally, they could be less cache-friendly than arrays or B trees due to pointer chasing and potentially scattered memory allocations, but modern implementations have improved that. Simplicity is often the main appeal.
Okay, makes sense. Now, Petrov's book raises an interesting potential problem. Log stacking. What's that about?
Log stacking. This is a subtle but important issue. Log-structured systems, like LSM trees, are used everywhere now. Your database might use an LSM tree. The file system underneath it, like F2FS, might be log-structured. And the flash translation layer, FTL, inside your SSD is effectively log-structured.
So you have logs on top of logs on top of logs.
Exponentially, yes.
Yeah.
And if these layers aren't aware of each other and don't coordinate,
Bad things happen.
you can inadvertently amplify problems you were trying to solve, like write amplification.
Rating the same logical data multiple times physically.
Yes. The database writes it. The file system might rewrite it during its own compaction. The SSD's FTL rewrites it during its garbage collection. You end up writing way more data than necessary, which wears out SSDs faster and can hurt performance. You also get fragmentation at multiple levels.
Yikes. So the layers need to be smarter.
Ideally, yes.
Yeah.
This leads to concepts like ALAMAs, latch-free, log-structured, access method-aware storage layers,
LMA. Okay.
and the general idea of mindful stacking. It's about making the layers cooperate. For example, some modern database structures like view trees are designed to be layered on top of something like LMA. The tree handles the logic, LMA handles the physical page management, garbage collection, and logging transparently underneath.
So the database focuses on its job, the storage layer on its job, but they coordinate.
Exactly. An even more extreme approach mentioned is open channel SSDs.
Open channel, what does that mean?
It means the SSD exposes much lower level control to the software. It lets the database or file system bypass the standard FTL entirely.
Direct control over placing data, managing where leveling.
Yes, you get direct control over physical blocks, parallelism within the drive, garbage collection scheduling. It's complex, but for a highly optimized system running something like an LSM tree, it allows the database to perfectly align its operations with the underlying flash characteristics.
Maximum performance by cutting out the middleman layers.
Essentially, yes, making the storage truly aware of the database's access patterns.
Wow, okay. That's deep. All right, so we've gone deep into single-node storage engines, B trees, LSM trees. But what happens when one machine just isn't enough? Massive data, huge traffic.
Right. Then you need to scale out, horizontal scaling.
Running your software on multiple machines connected over a network, but acting like one logical system.
Exactly. It's often way cheaper and more flexible than trying to build one single monster machine, vertical scaling. It's the foundation of cloud computing, really.
But it's not free, right? Going distributed introduces a whole new world of pain. I mean, challenges.
Challenges is the play term, yeah. Pain is often accurate, too, because when you go distributed, you slam headfirst into the inherent unreliability of the environment.
Things just break.
All the time. Communication links are slow, or they drop packets, or they fail entirely. Messages get lost, duplicated, reordered. Processes pause unexpectedly due to garbage collection or whatever. They slow down, they crash. Nothing is guaranteed.
This sounds like the fallacies of distributed computing.
Precisely. Those famous assumptions that engineers often implicitly make, but which are dangerously false.
Like assuming the network is reliable, zero latency, infinite bandwidth.
Yep. Or assuming topology doesn't change, there's only one administrator. A really critical one is assuming state consistency across all the nodes.
Thinking everyone sees the same data at the same time.
Which is almost never true in a distributed system without a lot of explicit, careful work. Data is always slightly out of sync somewhere.
So what's the takeaway for someone building these systems? Pray.
Prayer helps? Maybe. But mostly you have to actively design for failure. Expect it. Build defenses.
Like what?
Like implementing backoff strategies with jitter when retrying failed requests.
Jitter. Adding randomness.
If a server is struggling, You don't want all clients retrying at the exact same instant, hammering it again. Adding random delays, jitter, spreads out the retry load.
Smart. What else?
Robust checksumming, not just within a node like we discussed, but for data sent over the network. Verify data integrity before you process it to prevent corrupted data from one node poisoning others.
Building defenses at every layer?
You have to. To reason about this mess, we often use abstract models of communication links.
Models like...
Well, the simplest is maybe a fair loss link.
Oh.
Messages can be lost, they can be duplicated, but importantly, they can't be spontaneously created out of thin air. The sender gets no guarantee of delivery, though.
Okay, pretty unreliable.
Then you might have a stubborn link. The sender just keeps retransmitting forever until the message gets through. Guaranteed delivery eventually, but you might get duplicates.
Better, but duplicates are annoying.
Yeah. The ideal, what we often strive for or assume with protocols like TCP, is a perfect link.
Perfect. Meaning?
Reliable. Exactly once delivery. Now, exactly once is tricky. It really means exactly once processing from the receiver's viewpoint. Duplicates might arrive, but the link mechanism ensures the receiver only processes it once.
And it guarantees order?
Usually, yes. Like TCP uses sequence numbers to ensure messages are processed in the order they were sent. These models help us build more complex protocols on top.
Okay. And speaking of guarantees, or the lack thereof, the two generals problem, that always comes up.
Oh, yes, the classic. Such an elegant illustration of a fundamental limitation.
Remind us, two generals trying to coordinate an attack.
Right. Two armies, separated by enemy territory. They need to agree on a time to attack simultaneously. They can only communicate via messengers who might get captured. Message loss.
And they need to know the other general received the message and acknowledged it.
Exactly. General A sends a message, attack at dawn. Did it get through? General B gets it and sends back, okay,
Yeah.
dawn it is. Did that get through? General A gets the acknowledgement but thinks, does B know I got his acknowledgement?
It goes on forever. You can never be 100% certain the other side knows for sure.
Precisely. It proves that it's theoretically impossible for two parties to reach guaranteed agreement if their communication channel is unreliable and asynchronous. There's always that lingering doubt.
So how do we ever agree on anything in distributed systems then?
That's the multi-million-dollar question. And the answer is consensus protocols.
Consensus, getting everyone to agree.
Exactly. Protocols specifically designed to allow a group of processes or nodes to agree on a single value, like which transaction should commit, who is the leader, etc., even if some of those processes fail or are slow.
What do these protocols guarantee?
They typically guarantee three key properties.
Okay.
Agreement, all correct processes that decide on the same value. No split decisions.
Okay, unanimity.
Validity. If a value is decided, it must have been proposed by at least one of the participants. No pulling values out of thin air.
Makes sense.
And termination, all correct, non-failing processes eventually do decide on a value. The protocol doesn't just stall forever.
Agreement, validity, termination, the holy trinity of consensus.
Pretty much, yeah. They overcome that two generals limitation for a group under certain failure assumptions.
Okay, so consensus helps us agree. But to build systems that actually survive failures, we need redundancy, right? We need copies of data.
Absolutely. Which brings us to data replication, maintaining multiple copies of your data on different machines.
What are the benefits? Obvious one is fault tolerance.
Fault tolerance is huge, yes. If one machine holding a copy fails, the data is still available on others. High availability.
Keeps the service running.
Right. Another benefit could be reduced latency. You can place copies of data geographically closer to your users so they get faster responses.
Makes sense. Serve reads from a nearby replica.
But here's the big catch with replication.
Keeping the copies synchronized.
Keeping all those copies in sync is the central challenge. When you write data, how do you make sure all copies get updated? And what happens if you read from different copies while an update is in progress? This leads us straight into the complex world of consistency models.
And also the CAP theorem, right? That always comes up here.
Indeed, the CAP conjecture, or theorem, proposed by Eric Brewer.
What does it state again? Consistency, availability, partition tolerance.
It states that in an asynchronous distributed system, basically, any real-world network, you cannot simultaneously guarantee all three of these properties. C, strong consistency, specifically linearizability, acting like a single copy. A, availability, every non-failing node can always process requests. P, partition tolerance. The system continues to operate even if the network splits. losing messages between partitions.
And you have to pick two.
Well, the reality is network partitions P happen. You can't really choose not to have partition tolerance if you want a reliable system. So the real trade-off is between consistency C and availability A during a partition.
Ah, okay. So during a network split, do you prioritize keeping the data strictly consistent, even if it means some nodes become unavailable? CP system.
Or do you prioritize keeping every available node responsive, even if it means they might serve slightly stale or inconsistent data temporarily? AP system.
It's a fundamental design choice.
Absolutely crucial. And it's important, as Petrov notes, not to confuse this theoretical C-capo availability with general high availability like uptime percentage.
Yeah.
They're related but distinct concepts.
Gotcha. Okay, let's dive into those consistency models then. They sound like different levels of guarantees.
Exactly. They're like a contract between the database and the application. They define what guarantees you can expect when reading and writing data in a system with multiple, potentially diverging copies. They essentially limit the possible histories of operations that a client might observe.
What's the strongest model? The ideal?
The strongest and usually the most intuitive is linearizability, also called atomic consistency or strong consistency in the CPay context.
Linearizability. What does that mean in practice?
It means all operations appear to happen instantaneously at some single point in time and in a global, real-time order that respects the actual start and end times of operations, as if there was only one copy of the data and all operations were queued up and executed one after another.
So if I write X5 and then you read X, you must see 5 or something written even later. You can't see the value before my write finished.
Precisely. If one read returns a value V, all subsequent reads must return V, or a value written more recently than V. It implies this linearization point for each operation the instant its effects become visible globally.
Sounds great. Why doesn't everyone use it?
Because achieving it in a distributed system requires significant coordination, often involving consensus protocols for writes, which would be slow and reduce availability during partitions. It's expensive.
Okay, so we relax the guarantees. What's next down?
A slightly weaker, but still strong model is sequential consistency.
Sequential. How's that different?
With sequential consistency, all processes see all operations in the same sequential order, and the operations for any individual process appear in the order that process performed them.
Okay, so everyone agrees on an order.
Yes, everyone agrees on some sequential order. However, that agreed-upon order might not match the real-time order of operations across different processes. Operations from different nodes might appear interleaved in ways that wouldn't happen in real time.
A bit weird, but still consistent across observers.
Still quite strong, yeah. Weaker still is causal consistency.
Causal. That sounds like it cares about cause and effect.
Exactly. It focuses on causally related operations. If operation A logically happened before operation B, e.g. you read something, then wrote something based on that read, causal consistency guarantees that everyone sees A before they see B.
It preserves the logical flow.
It preserves that established cause and effect order, often using things like logical clocks, like Lamport timestamps or vector clocks, to track these dependencies.
But what about operations that aren't causally related? Like if you and I write to different keys at the same time.
Causal consistency allows those non-causal operations to be seen in different orders by different observers. It allows for some divergence. As long as causality is maintained, the system might need to reconcile these concurrent writes later.
Okay, getting weaker. This leads towards eventual consistency, right? But there's something in between.
Yes, a really interesting and practical middle ground mentioned is strong eventual consistency, sometimes associated with CRDTs.
Strong eventual. How's that different from just eventual?
It allows updates to propagate asynchronously, like regular eventual consistency, but it adds a crucial guarantee. When all updates do eventually arrive at all replicas, any conflicts that occurred are resolved deterministically to produce the exact same valid final state on all replicas.
So they all converge to the same answer automatically without ambiguity.
Exactly. The resolution is built into the data types themselves. This is often achieved using those conflict-free replicated data types, or CRDTs.
CRDTs, tell me more.
They are data structures specifically designed for replication, where merging different versions is mathematically guaranteed to be commutative, associative, and idempotent.
Meaning the order you merge updates doesn't matter, you always get the same result.
Precisely. Think of a simple grow-only counter. You can only increment it. Sending increments around, even out of order, will always result in the same final sum everywhere, or a last write wins register. The update with the newest timestamp always wins. A simple deterministic rule.
So CRDTs provide eventual consistency, but with guaranteed convergence to the same state. Very cool.
Very powerful for building certain types of collaborative or distributed systems.
Okay, and then the most common relaxed model, just plain eventual consistency.
Right. The basic promise here is if you stop making new updates to a given piece of data, then eventually all subsequent reads of that data will return the last value written.
Eventually. Could be milliseconds, could be seconds, could be longer.
Could be, yeah. The system doesn't guarantee when, just that it will happen eventually.
Yeah.
Conflicts during the convergence period are often resolved using simpler strategies like just last write wins based on wall clock time, which can be problematic, or sometimes using vector clocks to detect concurrent, conflicting writes that might need application-level resolution.
And this model often allows for tunable consistency, right?
Yeah.
Using N, W, and R.
Exactly. This is common in systems like Cassandra or React. N, W, R quorums.
Remind me, N is?
N is the total number of replicas for a piece of data.
What's W?
W is the write consistency level, the number of replicas that must successfully acknowledge a write operation before the coordinator reports success back to the client.
And
R
R?
is the read consistency level, the number of replicas that must respond to a read request before the coordinator returns the result to the client.
Okay, N, W, R. How do they give you tunable consistency?
The key insight is the relationship between W and R. If you configure your system such that R plus WN,
Read quorum plus write quorum is greater than the total number of replicas.
then you are guaranteed that your read quorum, R, and the write quorum, W for the latest write, must overlap on at least one node.
Ah. So when you do a read with quorum R, you're guaranteed to contact at least one node that has the absolute latest successfully written version because it was part of the W quorum for that write.
Exactly. By tuning R and W, you can trade off read latency, write latency, and consistency guarantees. If you set WN, you have very slow but consistent writes. If you set R1, W1, you have fast reads and writes but very weak consistency. If you set R plus WN, e.g. W majority, R majority, you get strong consistency but potentially slower operations.
It really raises that important question. How do you balance performance needs against consistency needs for your specific application?
It's a critical decision. Choosing a quorum, often a majority, N2 plus 1 for reads and writes, is a common way to balance. It allows the system to tolerate failures of up to N1 nodes and still make progress.
Vital for availability. And Petrov mentions witness replicas as a way to optimize this.
Yeah, witness replicas are a clever cost-saving measure. Sometimes you want a higher replication factor, N, for durability or quorum flexibility, but storing full data copies is expensive.
So a witness replica.
It participates in the quorum voting process for writes, but it doesn't actually store the full data payload. It just stores metadata, essentially recording, I saw this write happen.
So it contributes to the W count without needing the disk space for the data itself.
Exactly. It helps ensure consistency and durability guarantees by participating in the consensus or acknowledgement process, but with much lower storage overhead. Smart redundancy.
Very smart. Okay, so replicas can diverge, especially with eventual consistency. How do they get back in sync? What are the anti-entropy mechanisms?
Good question. Entropy is disorder, divergence. Anti-entropy brings them back together. One common reactive approach is read repair.
Read repair, fixing things when you read them.
Sort of, yeah. When a client issues a read request, the coordinator node might contact multiple replicas, maybe R replicas or even more in the background. It compares the responses it gets back. If they all match, great. If they differ,
Uh-oh. Inconsistency detected.
right. The coordinator identifies the most recent version, based on timestamps or vector clocks, and then sends update messages to any replicas that return stale data, bringing them up to date.
So it fixes inconsistencies for the data you're actively reading, kind of opportunistically.
Exactly. Cleans up as you go.
How can you make that more efficient? Fetching full data from R replicas seems wasteful if they usually match.
Good point. That's where digest reads come in.
Digest reads, using hashes.
Yep. Instead of asking all R replicas for the full data, the coordinator asks maybe just one replica for the full data and asks the other R1 replicas for just a digest, a hash of the data.
Ah, like the checksums we talked about.
Similar idea. If all the hashes match the hash of the full data received, then the coordinator assumes everything is consistent and just returns the data. Saves a lot of bandwidth.
But if the hashes don't match?
Only then does the coordinator go back to the replicas with mismatching hashes and request the full data from them so it can perform the read repair.
Much more efficient on the network in the common case where things are consistent.
Precisely. Now, About those hashes, they're usually non-cryptographic for speed. So collisions are theoretically possible, though rare.
Meaning two different data blocks could have the same hash.
It's possible. But usually, other background anti-entropy mechanisms like local trees will catch those more subtle inconsistencies eventually. Digest reads are an optimization, not the only line of defense.
Okay. Another trick mentioned is hinted handoff, often used with sloppy quorums.
Right. A floppy quorum means a write might succeed, even if fewer than W target replicas acknowledge it, as long as W total nodes, including maybe some non-targets, acknowledge it.
Okay, relaxing the rules for faster writes sometimes.
Yeah, prioritizing availability.
Yeah.
So what happens if the coordinator tries to write to a target replica, but that replica is down or unreachable?
The write would fail with a strict quorum.
But with hinted handoff, the coordinator might instead write the data to a different healthy node, one that's not normally a replica for this data, and leave a hint in that node's metadata.
A hint saying, hey, this data actually belongs over there.
Essentially, yes. This data belongs to node X. Please hand it off when X comes back online.
So when the original target node recovers,
The node holding the hint sees it's back and hands off the data, sending it over to the correct replica.
clever, improves write availability during temporary node outages.
Exactly. The downside is that if a client reads using a sloppy quorum before the handoff completes, they might read slightly stale data because the intended replica didn't get the write yet. Again, trade-offs.
Always trade-offs. Okay, what about finding inconsistencies in data that isn't actively being read? Background checks.
That's where Merkle trees or hash trees are incredibly useful.
Merkle trees, used in Bitcoin and Git too, right?
Yep, same fundamental structure. A Merkle tree provides a compact hierarchical hash representation of a larger data set.
How does it work for anti-entropy?
Each replica builds a Merkle tree over the data ranges it stores. The leaves are hashes of individual data blocks or key ranges. Nodes higher up are hashes of their children. The root is a single hash representing the entire data set on that replica.
Okay, a tree of hashes. So,
To compare two replicas, you don't need to transfer all the data. You just compare their root hashes.
if the root hashes match.
You know instantly the data is identical on both replicas with very high probability, super fast check.
If the root hashes differ.
Then you know there's an inconsistency somewhere. You then compare the hashes of the children of the root node. If those differ, you recursively descend down the tree, comparing hashes at each level.
So you quickly pinpoint the specific branch and eventually the specific leaf node data range that actually contains the difference.
Exactly. It allows you to identify and repair only the differing data blocks without having to compare the entire multi-gigabyte or terabyte data set. Massively more efficient for background consistency checks.
Very cool. Okay, beyond repairing differences, how do you just spread new information like cluster membership updates, schema changes quickly and reliably across a large system?
A very popular and robust technique for that is gossip, also known as epidemic protocols.
Gossip, like people spreading rumors.
Exactly the analogy. Imagine a node has a new piece of information, a rumor. It becomes infective. Periodically, it randomly picks one or a few other nodes, its neighbors, and tells them the rumor, infecting them.
And then they start spreading it to their random neighbors.
Precisely. The information spreads exponentially through the cluster, like a virus, a hopefully benign one.
What are the advantages of this? Seems kind of random.
The randomness is its strength. It requires no central coordinator. It's incredibly robust to node failures or network issues. If one path is blocked, the gossip will likely find another way. It scales very well to large numbers of nodes.
And it eventually reaches everyone.
With very high probability, yes. It achieves convergent consistency. Nodes quickly agree on recent events, and the probability of agreement on older events becomes extremely high.
What's the downside? Redundant messages.
That's the main one. A node might receive the same piece of gossip multiple times from different neighbors. It can be bandwidth intensive.
So can we make gossip more efficient?
People have tried various optimizations. One approach involves creating overlay networks.
Overlay networks, temporary structures.
Yeah, creating a more optimized temporary communication topology among the peers, maybe based on network latency or proximity. The book mentions plum trees, lazy push multicast trees, as an example.
Plum trees. Catchy name. How do they work?
They try to combine the speed of direct push with the robustness of gossip. Each node maintains a specific set of peers for eager pushing.
So it sends the full message immediately to a small group.
Yes, to its core eager push peers. But to all of the other neighbors, It does a lazy push.
Lazy push, just sending a hint.
Basically, yeah. It
Ish.
just sends the message ID or a small summary.
So if a node gets the lazy push ID and realizes it hasn't seen that message yet.
It can then request the full message from the sender or someone else. If it already got the full message via an eager push, it just ignores the lazy push notification.
So it builds an efficient tree for normal delivery, but falls back to gossip if parts of the tree fail.
Exactly. It aims for low overhead and low latency in stable network conditions, but retains the robustness of gossip for recovery during failures or churn, a hybrid approach.
Very clever balancing act. Okay, we've covered storage, replication, consistency, information spread. What about coordinating changes across multiple nodes, distributed transactions?
Ah, yes, the classic example, transferring money between two bank accounts that happen to live on different database shards or servers.
Got to make sure the debit happens on one machine and the credit happens on the other. Both or neither. Atomicity across nodes.
Exactly. This requires a new level of coordination. The most well-known classic protocol for this is two-phase commit, or 2PC.
Two-phase commit. How does it work? Phase one.
Phase 1 is the prepare or voting phase. A central coordinator node sends a prepare message to all participating nodes, the cohorts or participants, involved in the transaction. Each cohort tries to prepare the change locally. Year, for example, acquire locks, write intentions to a log, and then votes yes, prepared and ready to commit, or no, cannot commit.
Okay, everyone votes, then phase two.
If the coordinator receives yes votes from all cohorts, it decides to commit. It logs its decision and sends a commit message to all cohorts. They then make their prepared changes permanent.
And if even one cohort votes no or doesn't respond in time,
The coordinator decides to abort. It sends an abort message to all cohorts, and they roll back any prepared changes. All or nothing.
sounds reasonable. What's the catch? It's famous for having problems,
But
right?
the major drawback, the killer problem, is that 2PC is a blocking protocol.
Blocking, what does that mean?
If the coordinator fails after sending prepare, but before sending the final commit or abort decision, the cohorts are left hanging. They voted yes, they prepared their changes, locked resources, but they don't know the final outcome. They're stuck in an uncertain state.
And they can't just decide on their own.
Nope. They have to wait for the coordinator to recover and tell them the final decision. During this time, they might hold locks, blocking other transactions indefinitely. It can cripple availability.
That sounds pretty bad. Is there a fix? Like three-phase commit?
Three-phase commit 3PC was proposed to address this blocking issue. It adds an extra pre-commit phase and uses timeouts.
An extra step. How does that help?
The idea is that the extra phase provides enough information so that if the coordinator fails, the remaining cohorts can communicate amongst themselves and potentially reach a non-blocking decision, either commit or abort, based on timeouts.
So it's non-blocking. Why isn't it used everywhere then?
Well, it's complicated. 3PC adds more message overhead, more round trips. More importantly, it still doesn't perfectly handle network partitions. If the network splits during certain phases, different partitions might make conflicting decisions, one committing, one aborting, violating atomicity.
So it fixes one problem but potentially introduces another, more subtle one?
Pretty much. Because of its complexity and potential issues with partitions, 3PC isn't widely used in practice compared to 2PC or other approaches.
Okay, so if 2PC is blocking and 3TC is tricky, how do modern systems handle distributed transactions reliably?
Many modern distributed databases build their transaction protocols on top of consensus algorithms like Paxos or Raft.
Using consensus, how does that help?
Remember, consensus algorithms allow a group to agree on a value, even with failures. So instead of the 2PC coordinator being a single point of failure for the decision, you can use consensus to reliably agree on the transaction's outcome, commit or abort.
So the decision itself is made fault-tolerantly?
Exactly. Or some systems take different approaches, like the Calvin system mentioned in the book. Calvin uses consensus up front to agree on the execution order of transactions before they even start acquiring locks.
Agree on the order first. How does that help?
By predetermining the serial order, it dramatically reduces lock contention and deadlocks, simplifying the transaction execution phase.
Interesting approach. What about Google's Spanner?
Spanner uses Paxos extensively. It uses Paxos groups to consistently replicate the state of transaction managers across its globally distributed system, ensuring consistent decisions about transaction commits, even across data centers. Consensus is fundamental there.
So consensus isn't just for transactions, it's more general purpose.
Absolutely. Consensus algorithms are crucial building blocks for many aspects of reliable distributed systems.
Like what?
Leader election. agreeing on which node is in charge, maintaining consistent configuration metadata across a cluster, ensuring replicated state machines stay in sync. Anytime multiple nodes need to agree on something reliably despite failures.
Okay, let's talk about those consensus algorithms. Paxos was the big one for a long time, right? But notoriously complex.
Paxos, yes. Developed by Leslie Lamport. Brilliant, foundational, but famously difficult to understand fully and implement correctly. Even Lamport joked about it.
How does it work, roughly?
At its core, it works in two main phases. Phase 1 is about establishing leadership. Proposers send prepare messages with proposal numbers. Acceptors respond, promising not to accept lower-numbered proposals. A proposer gathers promises from a majority.
Okay, leader election phase.
Phase 2 is replication. The elected leader, proposer, sends an accept message with the chosen value and its proposal number. Acceptors accept it if they haven't promised a higher number. Once a majority of acceptors accept the same value, it's considered chosen or agreed upon.
And the learners.
Learners are passive observers that find out which value has been chosen by the acceptors.
Seems complicated already.
It is, and that's the simplified version. Multi-Paxos is an optimization where once a leader is stably elected, it can skip phase 1 for subsequent values, just running phase 2 directly, which speeds things up significantly.
Okay. Now, flexible Paxos. That sounds intriguing.
Flexible Paxos offers a really neat insight. It shows that the quorums needed in Paxos don't have to be strict majorities for both phases.
They don't.
No. Let Q1 be the size of the quorum needed in the propose phase, phase 1, and Q2 be the size of the quorum needed in the accept phase, phase 2. Flexible Paxos shows that as long as Q1 plus Q2n, where n is the total number of participants, you can still achieve consensus safely.
Q1 plus Q2n. So you can have like a small Q2 if you have a large Q1.
Exactly. You can require almost all nodes to participate in leader election, large Q1, but then only require a very small quorum, small Q2, to actually accept the value.
What's the benefit of that?
A smaller Q2 means the accept phase can potentially complete faster, with lower latency, because you only need to wait for a few nodes. You trade off slower leader election for faster replication, or vice versa. It allows tuning for different latency availability profiles.
Fascinating flexibility, but
Right.
still sounds complex. Which brings us to Raft.
Raft, yes. Developed by Diego Ongaro and John Ousterhout around 2013, its primary design goal was understandability.
A direct response to Paxos's notorious difficulty.
Absolutely. They wanted a consensus algorithm that was functionally equivalent to Paxos, but significantly easier to learn, teach, and implement correctly.
How did they achieve that?
By decomposing the problem differently. Raft defines very clear node roles: leader, follower, and candidate.
Leader, follower, candidate. Okay.
There's always at most one leader at any given time. Leaders are elected by candidates requesting votes from followers. A candidate needs votes from a majority to become leader.
Okay, clear leader election.
Once elected, the leader is solely responsible for managing the replicated log. It receives client requests, appends them to its log, and then replicates those log entries to the followers.
Log replication, so everyone keeps an identical log.
That's the goal. The leader ensures followers' logs become consistent with its own. An entry is considered committed once it's replicated on a majority of servers. Followers only apply committed entries to their state machines.
It sounds, more structured and easier to visualize than Paxos.
That's the general consensus, pardon the pun. Its focus on understandability has been hugely successful. Raft is now used in tons of major distributed systems,
Nice.
etc., used by Kubernetes, Consul, CockroachDB. Many prominent systems rely on Raft for their core consensus needs.
Okay, one last type of consensus for really tough environments, Byzantine consensus.
Right. Everything we've discussed so far, Paxos, Raft assumes crash failures. Nodes might stop working or messages might get lost, but nodes don't actively lie or behave maliciously.
They're faulty but honest failures.
Exactly. Byzantine fault tolerance, BFT, deals with the harder case, Byzantine failures, where nodes might be faulty in arbitrary ways. They could send conflicting messages to different peers, corrupt data, or actively work against the protocol. Think malicious actors or complex software bugs.
That sounds much harder to deal with.
Much harder. Algorithms like Practical Byzantine Fault Tolerance, PBFT, are designed for this.
PBFT, how does it work? Does it need more nodes?
Significantly more nodes, yes. To guarantee safety, correctness, and liveness, progress in the face of up to F Byzantine faulty nodes, PBFT requires a minimum of 3F plus 1 total nodes.
3F plus 1, why so many?
Because the honest nodes need to be able to outvote the potentially faulty malicious nodes and reach agreement amongst themselves. Nodes essentially cross-validate messages they receive from others. With three F+1 nodes, the F-faulty nodes can't form a majority, which would be F+1 or more, to trick the two F+1 honest nodes. The honest nodes have enough redundancy to identify and ignore conflicting or malicious messages.
So you need over 2/3 honest nodes.
Correct. It's much more expensive in terms of the number of replicas required and the message complexity, more rounds of communication for validation. But it's absolutely essential for environments where you cannot trust all participants, like public blockchains or highly critical control systems.
Wow, so that covers a huge amount of ground,
Yeah.
from single node storage with B trees and LSM trees, all the way to distributed consensus with Paxos, Raft, and even BFT.
Yeah, it's quite a journey through the internals. We saw how fundamental ideas like buffering, immutability, ordering, and trade-offs between consistency and availability appear again and again at different layers.
We unpacked replication strategies, consistency models, from linearizable down to eventual anti-entropy mechanisms like Merkle trees, gossip protocols.
It really highlights that while the specific technologies evolve rapidly, the core computer science principles underpinning database design are remarkably timeless.
And learning this theory, even at a high level, helps you understand not just how today's systems work.
But also why they work that way, and how new innovations are likely to build upon these same foundational ideas, always balancing those complex trade-offs.
Absolutely. The elegance and, frankly, the sheer cleverness hidden beneath the surface of the software we rely on every day is just astounding when you start digging. We really hope this deep dive inspires you, the listener, to maybe apply this same curious, analytical mindset to other technologies you interact with.
Yeah, what other black boxes are out there in your daily work or life?
What hidden complexities are lurking, and what might you understand differently if you could peek inside? Until next time, keep digging, keep learning, and keep asking that fundamental question: how does that really work?